Hi, this is Make a Geek and I'm Dan. In this week's video I'm going to talk through some of the code that goes behind the linear motion rail that I talked about in the last video. I'm just going to step through how it looks like. You can see it here on the left of the screen. It may seem a little bit daunting at first. Hopefully as I talk through it will be clear that it's really just a few different concepts layered up on top of each other to provide all the capability. So let's dig into the code and take a look through. Hopefully if you make this full screen you should be able to see the individual lines. In this first section we have a definition of the various pins that we want to use and given them variable names to help us identify what we're using them for. So there are quite a few, but we have essentially a pair of pins 2 and 3 we're going to use for direction and step instructions to the first stepper motor. Then pins 4 and 5 we'll use for direction and step instructions to the second stepper motor. Push button 8 is what we're using to take input from the end stop switches. So either end connected to the same pin will trigger the same behavior because we just need to flip the direction. Then we have pins 9, 10 and 11 that I'm just using to provide a way of inputting some selection control. So rather than have to change the speed by reprogramming it, the Arduino I can just essentially set some jumper connections to select the speed that I want to use. So then we have a few starting counters, so variables that we use to sort of record where we're at during execution of which direction, how long it's been since we turned, and kind of the overall delay speed of the algorithm so that we can control how fast the other things move. So setup is where we take all of those values, all the pins we want to use, and tell the Arduino how we want to use them. So the first 4 here are all defined as input pull-up, and what that means is that if I connect them, by default they essentially live in a high state of 1, and if I connect it to ground then they drop to a low state of 0, and I can read those different states in the code. So that just makes it really, really easy. I can just wire through a switch to ground, and whenever I hit the switch, it triggers the desired behavior. Then we have 4 output pins, and as I mentioned before, that's the direction and step pair for each stepper driver. And then we have some code to just set the initial state of the direction of each stepper to the same direction. And then the last thing here isn't actually necessary in normal operation. This connects to the serial output, so when you're programming an Arduino, if you have it connected to a computer, you can actually have it output information to a console, which helps you to debug and understand what's going on. So I could actually get rid of this line, but you'll see later on I have sort of various output statements that I was using whilst I wanted to just check that my logic was working correctly. One thing about electronics is that it can be very difficult to understand what's not working if you get something wrong. Often you get no real feedback because you made a mistake, so it's really, really helpful to be able to run in that mode. So then we get to the main loop of the code, and so in this first state what we do is read the current values from all of those input pins. So button state to find out whether we have tripped any of our end stops, and then the other pins for our mode inputs, which I've designated as 1, 2 and 4 because I'm using them in essentially a binary pattern, so I consider them to be the first 3 bits of a binary number, so I can essentially select 8 different possible states with just those 3 pins in different combinations, and that's what this next piece of code is doing. It's basically just a fairly inelegant way of saying checking for each of those 8 different states, and whichever one it is, it designates a speed for the loop which controls how fast it is. So a low number means we're going really fast, we're not waiting around the loop, and a really high number at the end here, 4000, that means we're waiting 4 seconds after executing the loop before we go around again, so that we can have a really, really slow movement. That's really good for those slower time lapses. So having gotten our mode inputs, we've also queried that end stop state, and I have a piece of logic here which again maybe looks a little complicated at first sight, but I'll just walk through it. Essentially, if the button state has gone low and now equals 0, then we know that the button has been triggered. I'll come back to this second part in a moment, If the button has been triggered, we just set the state on one of the Arduino built-in LEDs just to flip it back and forwards to give an indication of its direction. And so essentially, if we were previously heading in direction 0, then switch us to a high state on the direction on both steppers, and set direction to 1. And if we were already direction 1, we flip it the other way around, we make them low state, and keep direction 0. So this really does just flip-flop between them. Now the interesting parts of this are this last switch counter. So what I'm doing here is I'm keeping track of what position I was at last time I flipped direction. And the reason I do that is to track how far off from the last time I switched, how I'd gotten. Now, this would seem like you wouldn't need to do it, because in a theoretical world, you think, well, you come along, the switch is high, you hit the switch, it goes low, you switch direction, you move the other way, the switch comes off. Now, that's great in theory, but in practice, you're going around this loop a hell of a lot faster than you really can imagine. And so there are actually a whole bunch of values you're getting as you press the switch down and as it comes back up, and it's not actually guaranteed that it'll always smoothly transition from off to on and back to off. You might actually get some weird readings in the middle where you're kind of off and then on and then off and then on. And so what that can do is cause a load of problem for this logic, where it sort of flips back and forwards when it's really only in the process of pressing one button. So this tracking this counter, I just set an arbitrary number here of 200. I just ensure that I've moved a certain amount back in the other direction before I'm interested in listening to the switch to come back again. And that just helps avoid that situation where you can get some weird, unclean readings. So having done all of my basic setup, controlling whether I hit the end, it's time to actually tell the stepper motors to do something. And the way you do that with the easy drivers that I'm using is to have a pair of writes to the step pin to set it to low and then high. And all it's doing is it's detecting that transition between one state and the next to say, oh, okay, that's a pulse, and I now step. So we do a pair for the main linear motion, and then we do some logic to decide whether or not we also want to do the panning motion. So for my setup, I really wanted the pan to track to the center, so it would always be kind of turning to point at my subject. And so I don't need to turn it as often as I need to turn the motor that moves us back and forth. In my case, I figured out I could do basically out of every 32 times I tell the linear motion to move, I only want to move my panning motion half that amount. So the reason I chose 32 is because the stepper motor is doing 1/8 microstepping, so it actually takes 8 step signals for it to do a single rotation, and I wanted to do 2 of those in a batch. I probably didn't need to do it this way, but that's what I did. So essentially, for every step number that's cleanly divisible by 2, I do the same low-high step signal to the pan motor. Then when I get to 32, I go to 0 again. There's one delay that I always put in, which just makes sure that we've definitely written those signals to the pins and given the driver enough time to react to it. And then I increment my counters to that the rest of the logic is using. And the last thing we do is essentially go to sleep for however long we need to make the motion as fast or as slow as possible. So that's all the code. I say it's not really very long. At first glance it looks a bit complicated, but it really does, like the Arduino really does make this pretty simple. You can use those digital inputs and outputs, you can read their states really easy, you can push out information to them. Super simple. Now my circuit is a little bit more complicated than it needs to be. You can get Arduino shields that will control stepper motors, which would kind of take a lot of my mangled wiring and keep it together in a nice place. But I actually have 2 individual easy driver stepper circuits, which are pretty easy to control, using point-to-point wiring to connect everything together. So I hope this has been helpful. If you enjoyed this video, don't forget to hit the like button and subscribe if you'd like to see more of this in the future.